Okay, hello. Today is June 22nd, and today we are going to start with exercises number 14 and 15. So you have your lecture notes in front of you, and on page 391 or so, there should be the tasks for today. You got it? Okay. Now, the first question is popcorn effect. Describe the causes and the failure mechanism. So, and the second part could be regarded as part of that question. List the 3 failure criteria. Yes, popcorning is a failure mechanism. So first of all, we should try to understand what leads to that phenomenon. In fact, it's really a complex phenomenon, and we could first start, for instance, with a lead frame. Here is the lead frame. The leads maybe are not so important here today. And to that, here we have a molded package. And we have a chip here. That chip has been glued. We have wire bonds. Okay, that's the package. And what is popcorning? Popcorning is a phenomenon when we go into soldering, and in the soldering we get cracks or bulges or evident damages of the device in the soldering process. And there are several phenomena which are important here. The first thing which is important is the CTE mismatch between what? Can you give me information what has mismatch altogether? Okay, I'm waiting for answer. Which kinds of mismatch do we have here? So we have silicon lead frame with which other mismatch do we have?
So we have also the package, the molding, and also the silicon.
So the molding compound against the silicon, and what else? What is the third? The lead frame. So that silicon lead frame is not our concern today because it's typically a damage between the molding compound and the other components. And in that way, what's the consequence of lead frame, of mismatch? The consequence is mainly stress. And stress can lead, for instance, to delamination. What is the second important phenomenon which is a condition for popcorning? In real popcorn, what leads to the popcorning? Yes, it is water. In fact, we must say it is not so much the water in the molding compound, but the molding compound takes up, let's say, 0.1% of water by weight. But the main thing is that the water penetrates and the water migrates to interfaces. So that's the problem. And interfaces often are not smooth, but they have they also have impurities. So the problem is that we have a small accumulation of moisture in interfaces. In fact, that can lead even to, let's say, moisture films in interfaces below 100% relative humidity. So, water uptake, even below below 100% relative humidity. And we have condensation on interfaces. These lead to a certain amount of water. So a higher of water. And also the interfaces are weakened by this. Weakened. So now when we go into the soldering process, what is a typical soldering temperature? Can you please speak a little louder?
260 degrees centigrade.
Yep. Let's say up to, some soldering processes are a little lower with respect to temperature, let's say up to 240 to 260 degrees centigrade. So in some standards we use 260 as a reference temperature for the soldering. Heating, fast, let's say more than 100 degrees per 10 seconds. So that's a relatively fast rate. So what will happen to the water? The water will evaporate. If we would heat very slowly, we could reversely drive out the water out of the molding compound. So it would be a drying process. But if it's fast, we have a large increase of internal pressure. For instance, already 2 bar at roughly 120 degrees centigrade, but we go even higher, so the pressure will be significantly higher here in that case. Yes, and now you have to keep in mind we also have the stresses from the manufacturing, and that means high internal stresses. And especially, so expansion of the water, and that mainly leads to cracks, bulges, and other secondary damages. What could be such a secondary damage? For instance, wire bond lift off or so. Okay. So what are remedies against such popcorning? Yes, what would you do in order to avoid popcorning? Have you an idea? Come on, think about it and talk.
Using a package that has good film efficiency.
Yes, so good CTE match. Generally, smaller packages are better. When you talk about stress problems in assembly and packaging, there is a simple rule of thumb. You could say the bigger the package, the bigger the stress. Yeah? Smaller devices have typically less stress problems. Smaller packages, then you want to have a good adhesion. Of the molding compound against the silicon and lead frame. And the last thing is also avoid impurities. On the surfaces. The main reason for this is that often impurities can be hygroscopic. That means they take up humidity even at low moisture content in the air. So cleanliness is of utmost importance in order to avoid many problems, especially also corrosion problems in assembly and packaging. So now we can go to number 15. What is a failure criterion in popcorning? So that means, how do you decide you have a failure? Can you give me a guess? When do you say, sorry?
If the shell gets break.
Okay, so if it's broken in some way, yeah, so, or cracked, so cracks is one criterion, and one is on the outside. Bulges of the package. internal cracks. What else?
I think you can see also the electrical failure because of the interconnection damage.
For electrical failure, let us say there would be mainly 3 different criteria, and that is also important for your future work. How can you define it as a electrical failure? So you said wire bond broken, that means an open, yeah? What's the opposite to open? Yeah, it's a short circuit then, yeah? And also it could be a parametric failure. That means you test the devices. For instance, you have a, let's say, operational amplifier, and you test for the amplification factor, or in another device, the attenuation or something like that, and this property is no longer achieved. Yeah? It could also mean that it is still achieved at room temperature, but no longer at high temperature operating live test or so. And that means the device must be more or less as good as it would be without such popcorning. Also, we must say such soldering tests are also important in all other reliability tests, for instance, temperature shock and so on, because before we go into such tests, the device must be always subjected to soldering cycles. So that's, you could say, that's something like a very big shock in the beginning of the device's lifetime, and that could already lead to some damage, which becomes apparent in later tests. And so this initial soldering with a standardized profile is not only in popcorning important, but also in many other reliability tests. Okay, so number 17 we already had. Number 16 we did not yet have. That's the packaging steps in pre-molded packaging. Okay. What is pre-molded packaging? Can you, that's also important, you know about this. What is pre-molded packaging? What does, so, how do we produce yeah, go ahead, please.
It's the use of injection molding for the packaging process.
Yeah, so it is injection molded packages. And what are the 2 or 3 main constituents of that package? We have the package body, And what's the material of such package body? Do you have an idea? Sorry? Yes, generally a thermoplastic material. So that means just simply if you heat it enough, for instance up to 250 or 300 somewhat degrees centigrade, it will be molten. Yeah? So all materials you now use for 3D printing are where we have a fusion process, you typically use thermoplastic materials. So we have the lead frame, and of course it's typically for copper alloy. Okay, I don't know what's going on here with this writing. Yeah, so we have the packages, and the third thing we might have is a heat sink. Oh. We haven't shown that explicitly in our lecture, but that could also be a part. For instance, we have some material which is injection molded. It is molded around the lead frame. So today, let's make it simple. We only have a lead frame to one side, and then we could show, for instance, the bottom could be some different thing. So that could be, for instance, some heatsink material. For instance, that could be a metal plate or such a thing. And now what do we have to do? We have to mount the chip, and typically, what's the process of mounting the chip? What do we need to mount it? Yeah, not only adhesion, but adhesive we need, yeah? Okay, so we need an I should have left it. We have an adhesive. For instance, you could use a needle dispenser or a printing. Or a screen print. Screen printer is not so easy when you have to put it into some cavity. Okay, so the next is we pick and place the chip. What's the next thing we have to do? Yes, glue curing, very good. And in the exam, I will always ask for, or I will not specifically ask, but I will expect that you give me information on the curing conditions. Have you an idea how you could do this? For instance, you could start, let's say, there are many possibilities. But for instance, one thing would be 180 degree centigrade, let's say 4 minutes, yeah? And every 10 to 20 degree, you must double the time, yes? So then you could say something like, just as a guess, 100 degrees centigrade, 4 hours or so, yeah? That could be typical, or you can select something in between, yeah? So typically, if you have a chemical process with an activation energy of 1 electron volt, which is some kind of standard value, you could say the rate doubles every 10 degree, or the time is divided by 2 with every 10 degrees. So you could say 170 is 8 minutes, 160 is 16 minutes, 150 is half an hour, 150 is 1 hour, 140 is 2 hours, 130 is 4 hours. But it's not precisely doubling, so just to get a guess, but I would like that you have an idea, yes, which is somehow reasonable. Okay, so after we have done the curing, we go into the wire bonding. Here is no wire bond. Description of wire bonding will be a separate thing. So we do wire bonding. Also, maybe I should just show it here. Typically, when we have a lead frame, that lead frame is always covered with some nickel gold, for instance. You cannot wire bond with gold directly on copper. That has several disadvantages. So we always have nickel gold, nickel several micrometer gold, a fraction of a micrometer, typically below half a micrometer, because gold is expensive. So we have the wire bonding. Did a small mistake. What the next thing we can do here? Are we finished now? Yes, so I check. Why doesn't? Okay, so we have it's not silicon but silicone. Come on. I don't know what's going on. Unfortunately, it ceased to. I don't know. Excuse me, but I don't know. It's not my fault. Okay, we have the silicone, and after that we have to close it. How do we close it? We have to, we put on a lid. I don't know why there's such a lag. Now it comes. And here we have to weld in some way, and that could be done so. First we have the silicone, potting, and as a last we put on, so we pick and place lid, and we do some fusion welding. So we could use a hot element. We could use a laser. We could use ultrasound. And in that way, we have finished our package, and that's the complete process. So it could be necessary in the exam that you have some pre-molded package for the system, and in that way, at least we know the sequence of the processes, and in the exam also you will be requested for more details of the process. For the chip gluing it was simple, so we already had it. But for instance, for the wire bonding, this might require a separate description. Okay, so that was number 6.
I have one question.
Yeah, go ahead.
For the heat sink, where we put the heat sink?
Yeah. For instance, imagine you have a module, and that module dissipates high power, and in that way, the chip must give away lots of heat. If you have a pre-molded package, a plastic material, let's say like PA66 or LCP, that has a very pure thermal conductivity, let's say something between 0.2 and 0.5 watt per meter Kelvin. On the other hand, when you use something like a heatsink of aluminum oxide, that would have a thermal conductivity of 25. So it's 100 times better. But of course, that heatsink must be attached. So one of the processes to attach such a heat sink is just by some gluing process. Yeah. So we fabricate the package separately, and later on we glue them together. You could also use a glue and additional screwing or such. Yeah, many plastic packages have some kind of a heat sink, especially in power electronics. Did that answer your question?
Yes.
Okay, number 17 we already had, so let's proceed with number 18. No, we are not so far in the lecture, so I will do it on the next Monday. But the next question, you could already have an idea. Describe a CTE-affected failure mechanism for substrate material of printed wiring boards. What are the failure causes? Make a sketch and a quantitative evaluation of stress. That's also something very interesting. in order to describe which problems we might have. So, CTE in the CTE problem in a printed wiring board, what are the materials involved in a printed wiring board? Can you give me a hint? Yeah, but what does it consist of, this printed wiring board? No. We are talking about printed wiring board or printed circuit board, like as often it is named FR4. Yeah, what was it? Copper? What else?
Glass, fiber, resin, and copper.
Yeah, I couldn't hear, but I just said it's glass fiber.
Yeah, and resin.
Yes, typically epoxy. Yeah, so if you don't know about which material you use in assembly and packaging, you always say epoxy. In 95% it's correct. There are different epoxies, but one will fit. Okay, so what is acting here against each other? We have two things. One is the glass fiber and the epoxy can be regarded as one fiber reinforced material, and in between we have the copper. So what would be the CTE of that material here, of that fiber reinforced? And now we have to distinguish. And what is the CTE of copper? Yes. Okay, that's fine. Okay, 17 ppm per Kelvin or 10 to the power of -6, I agree. For this material, we have 4 CTE values, roughly. Can you give me an idea why we could have 4 CTE values?
We have a different direction, X, Y, and Z, and also the transition, class transition temperature.
Okay, yes, we have X, Y, Z. And what else do we have? We have below TG and above TG. What is a TG? Can you? Yeah, good, but what is the origin of that glass transition? Can you give me an idea what it means, maybe on a molecular basis? No, it is not a liquid phase. Definitely not. We have another transition, for instance, in thermoplastic materials, which is first glass transition and then melting. In duromeric materials, which is a resin that has been hardened, we have no melting. But if you make it too hot, it will just flame off, or it will go up in smoke, yes? The glass,
The temperature after which there is an exponential change in its properties.
it's not just exponential, but it's a strong change. And the main reason is the bonds in a polymer are typical covalent bonds, which have a strength of several, let's say, typically 2 to 3 electron volts. Yeah? So that means to break that bonds, you have to bring up an energy of 2 to 3 electron volts per bond. And normally in such a material, just by temperature, you cannot break, or you will not break these bonds before it goes up in smoke. Yes. On the other hand, you have another type of bonds, which is physical bonds, or maybe you heard about van der Waals bonds. And these bonds, they will lose their strength at higher temperatures. And so the strength of these bonds, which is only in a fraction of an electron volt, is lost. And that means all the molecules become more mobile against each other. It is like gluing together spaghetti with a fat sauce, yes? When you glue it together, it can be like a stiff lump, yeah? You heat it, this glue, it melts, and only the spaghetti, but they are still spaghetti. That's the idea of glass transition. And in that way, it's also a reversible process. So now, also printed wiring boards have a glass transition. And typically, you could say, for instance, below Tg, it could be a typical value of 12, yeah? In XY direction. The CTE above Tg in plane is not defined because that will also not increase because the fibers contract again because the material is so soft. The fibers cannot be held by that resin. So above Tg in XY, you will not find it, but in Z direction, you typically have a 3 to 4 times higher CTE. So let's say here it could be something like 40. On the other hand, if you still increase the temperature beyond the glass transition temperature, again, a factor of 3 or 4 increase is found in the glass above the glass transition, and so we could say maybe here it would be something like 150. Altogether, 10 to the power of minus 6 per Kelvin. That's always the units. And now, where is the biggest problem? We can see here it is above. No, sorry, I made a mistake. That was I wanted to do another circle. That's the biggest problem here. Between the copper and the resin and the FR4 or the material above Tg in Z direction. And when do we have that problem? That problem we typically have in soldering. So, T is larger than Tg. That's one of the problems. And the second problem is in temperature shock. for instance, minus 40, 125 degrees centigrade, because here we have a continuous heating and cooling, and for instance, we can have it 1000 times as a typical value we have here. Okay, but what is a structure which is most sensitive now? And I can make a small sketch.
The powerful ear holes.
Yes, that's the via holes. And typically it's like this. And also what we have is frequently, or in almost all printed wiring boards, some intermediate layers which are attached. Okay. Typically, of course, they should be attached continuously. So maybe it's better to make it that way here. And now what happens when we heat it? Yeah, I first have to put in the resin. And now we heat it to 260 degrees centigrade. What will happen then?
We can see the crack in the corner.
Not yet. We must go stepwise in order to analyze the problem. Yeah. So always there is a method saying failure, cause, and effect. So presently we are still with the cause of the failure. And what happens is the following. So I would say the bottom would be constant. It expands in a way, it looks like this after the heating. And that would mean we have strong forces. No, that was not so beautiful. Okay, in that way, so the whole thing is strained into that direction, and also on the bottom the same happens. So now what is when we go from room temperature, we could ask, what is the strain difference we have here? So the thermal strain difference is how much? Delta alpha times delta T. In our case, delta T is how much? How much is it? Sorry? 260 not, but 260 minus room temperature. For instance, we could say 240 degrees centigrade. Yeah? Okay. What is a delta alpha? That's 100. Sorry? One. Yes, it's 150 minus 17 is 133 times 10 to the power of minus 6 per Kelvin. Okay. Normally, if we would do it really correctly, we first would compute the strain difference from room temperature to Tg, and then the strain difference from Tg to soldering temperature. But here we do it all together. Okay. Now that's a system where we can say the copper, it is a very thin structure. The copper will take up all of the strain. And that means the consequence is the elastic strain in the copper is the same like the thermal strain difference. So it's a relatively simple case. And that is how much? 133 times 240 times 10 to the power of minus 6. So that is 2.5 times 1.2, so 2.4. So it's roughly 3. Yeah? 3 times 10 to the power of minus. Was that correct? 240? Oh yeah. Yes, that was a mistake. Yes, I was just wondering why that number had the wrong exponent. So, and that is in terms of strain, 3% of strain. 3% of strain, is it much or not much? It is a lot. So, what's the stress in the silicon, in the copper now? What's the equation? What is the stress when you know the strain? Which property do you know? Yeah, okay, very good. So, and that Young's modulus is 120 megapascal, 120 times 10 to the power of 3 megapascal, 120 gigapascal, but we work in megapascal times. So the stress is 360 Is that realistic? Is it a low value or a high value? Yeah, it is too high, and the reason is we just did only purely linear elastic computation. So normally, so here we have the Young's modulus, stress, strain, but typically when we go to this, we have, for instance, that offset here when it yields. So that's typically 0.2%, just that offset. And that material yields, yeah? That's a yield limit. And here we have plastic deformation. So only a small part of the deformation is elastic, maybe up to, just as a guess, let's say 150 megapascal for pure copper, and then it yields, and then it is a deformation with only a slight increase. On the other hand, if we reach here something like 3%, it could still survive, but it doesn't survive the cycles afterwards, because in every cycle we get a small increment of plastic strain, and finally this cyclic strain sums up to a value which is beyond the fracture limit, and in that way it will survive the soldering because the copper can yield a little, but afterwards it will fail in temperature cycling. So, okay. But on the other hand, we can see we have done an estimation. In fact, that was a very crude simplification. In our model, for instance, the thickness of a printed wiring board doesn't have an effect on the numbers of cycles to failure. In fact, that's not true. You could again say the bigger the part, or in this case, the thicker the part, the bigger the problem. So thicker printed wiring boards have less cycles to failure until we get, and that's the failure, we get either cracks here or the deformation is so large we get here some crack between this internal layer of the printed wiring board and the wire metallization. Okay, in that way we have analyzed the problem, and as I mentioned before, it is always good if you analyze such a problem, and you will in your further career. It's always to go look and to distinguish what are causes and what are effects, yes? First things first. Okay, in that way, yeah, maybe we have a few minutes, if you have time. We ask for surface finishes for printed wiring boards. Can you explain to me what a surface finish is? What the purpose of such a finish is?
I'd say that the purpose of the surface finish is to protect the material, for example, from oxidation. And if we have to solder or wire bond, maybe the surface finish would be to apply material that works for the connection. So we can glue on it or solder.
Okay, so that was very good. So again, as I like it, not to know such a thing, but also to know what's the background. So protect from oxidation. The big disadvantage is solderability. can be impaired, so that could be a problem. And the next is bondability. With wire. And also glue. Must be gluable. So, okay. And now the question is, what kind of finishes do we have? What's the easiest way? So it's always, of course, on copper. What's the easiest way is to do nothing, but then we will have the problem. What's the easiest thing we can do?
Using a solder mask.
No. The thing is, the solder mask is not there to do this protection and to preserve solderability. To the contrary, the solder mask is on the copper in order to avoid it is wetted by solder. Yeah? You have solder mask in places where you do not want to have solder material under no circumstances. Okay. The easiest way would be to have some organic coating. I would say it's not really a wax, but it's something which is wax-like. So also it will melt away or just evaporate during soldering. It's a weak. The next is hot air leveling. That means dip in tin, in liquid tin, of course, and blow off the excess solder. What is the most important process we have now for tin coating in printed wiring board? No. The disadvantage is in electroplating you must connect all metallic surfaces with a cathode, yes? And that you cannot do because all metal strips and so are individual, yes? You would have to connect them, then you can electroplate, and then you remove this central connection. That's not a good thing. We use chemistry. We use chemical metallization.
The process of etching, maybe?
Sorry?
The process of etching, where you...
No, you do not etch. It's the contrary. You put it in a special solution of tin, and the tin is deposited. You can imagine it like electroplating without external electrode. So, in fact, the copper surface is both anode and cathode. And in that way, we can have a reduction process, and we can create a tin deposition. So it's a chemical tin. So we just dip it into the soup, yes? So, sorry, what is your question? Yes, so chemical deposition, we also call it electrolysis. Contrary to electrodeposition, but nevertheless, the name electrolysis is not quite correct because it is an electrochemical process we have here. So the next we can have is what is, I would say, most important, and is nickel gold. That is also typically electroless. Also, we must not imagine we just dip it in one bath or in two baths, but there are several solutions into which we must go subsequently. But we have nickel gold. The nickel is in the micrometer, and that gold is in the significantly below micrometer range, as we already said. What else can we have? We can have, for instance, silver plating. For the silver, we can also have electroplating, because silver in most places only is put on, for instance, on certain spots, but in most cases it's also electroless. So, and instead of nickel gold, we can also have something like nickel palladium, which is very similar. Okay. One thing to answer. On this wax, we can only solder. On the hot air leveling, we can only solder. On the chemical tin, we can only solder. On the nickel gold, we can glue, solder, wire bond. And on the silver plating, we can glue and solder. We do not wire bond on silver because its properties with respect to corrosion resistance are quite poor, so we avoid this. Do you still have questions? Okay, today it took us a little longer. I think maybe it makes sense to take longer than 3/4 of an hour here, and so some of your guys send me questions from time to time, which I also answer. And so you are free, if you want to know something, just send me an email and I will try to give you explanation. So, okay, for today.
I have a question.
Go ahead, please.
General question. The script you wrote to email that we can pick up printed script.
Yeah.
Is that correct? Because I went, where do we find them? Because I went there and I couldn't find them.
Yeah, okay. You go into building 103. Then you go into the first floor. And then the third office on the right is mine. You do not enter this, but you turn around and behind you there is a rack. And in that rack you find the lecture notes, and you can take one for you and another one for another student, yeah? But no more of these.
Okay.
Was that clear? Okay.
In building 103, first floor, third office, left, opposite of the floor.
Opposite, yes. Okay. So please, if you don't find directly, search for it. Sometimes we are out of it. Then you must contact some of my staff, and they will reload this rack with other lecture notes. Yeah.
Who should we contact for that?
One of my staff. They have their offices, but I don't want to be disturbed just for lecture notes. Yeah. Okay. Thanks for your attention, and see you. Goodbye.